Direct, authoritative tone. Algorithms do not replicate human cognition. They possess zero biological adaptability. Instead, they execute rigid mathematical optimization. If you take an algorithm trained on a fixed set of inputs and slightly distort them, the output is likely to be completely wrong. The machine cannot extrapolate beyond its previous experience. Unless it receives explicit mathematical instructions on how to process that specific physical distortion, it will fail. What a learning machine actually does is blindly search for a mathematical formula. Its only goal is to find an equation that maps a collection of given inputs to a set of desired outputs. We call these initial inputs training data. Training data is the raw numerical information used by the algorithm to derive and anchor its mathematical formula. The algorithm evaluates its success strictly based on a predefined mathematical loss function. A loss function is a mathematical measure of the penalty for making an incorrect prediction. It does not use intuition. It simply calculates the penalty. True machine learning is an illusion. The entire process is simply the mechanical fitting of parameters to minimize error within a highly constrained, predefined environment. If the process is nothing more than parameter optimization, why does the entire industry use the biological term learning? The answer is marketing. Arthur Samuel, an American pioneer in computer gaming, coined the term in 1959 at IBM to sound futuristic and attract attention. IBM used the cool new phrase machine learning to attract enterprise clients and talented employees, functioning exactly like modern corporate buzzwords such as cognitive computing. In modern engineering, the word learning is universally understood to be used purely by analogy, not as a literal description of the machine's capabilities. To master this field, we must abandon biological metaphors and embrace the high-dimensional geometry that actually drives prediction. The foundational engineering problem is translation. How does a machine process a real-world, unstructured entity, like a text-heavy email? The bag of words method converts text into numerical features using a predefined dictionary of 20,000 English words. The first feature is a 1 if the email contains the word "a," and a 0 if not. This continues down to the 20,000th feature, Zulu. This mathematical structure is a feature vector, an ordered list of numerical values describing a single example. Because it has 20,000 elements, it dictates a specific coordinate point in a 20,000-dimensional geometry space. We repeat this procedure for a collection of 10,000 emails. This creates a dataset of 10,000 plotted points, with each point labeled +1 for spam or -1 for not spam. Data preparation is an act of geometric translation. We convert human language into a spatial coordinate system that an algorithm can navigate. Now we apply the support vector machine, or SVM, algorithm. An SVM classifies data by finding an optimal dividing boundary. Its objective is to cleanly separate the +1 points from the -1 points in this high-dimensional space. This plot shows the algorithm's solution, a decision boundary. In our 20,000-dimensional space, this boundary is a 19,999-dimensional hyperplane slicing through the data clusters. The mathematical equation for this hyperplane boundary is exactly w.x minus b equals 0. The core parameters defining this plane are w, a real-valued vector of the same dimensionality as our input, and b, a real number scalar. To classify a new email, the model runs the equation and checks the result sign. A positive result is classified as spam, and a negative result as not spam. The algorithm satisfies a strict constraint, forcing all examples to the correct side of the boundary. This creates the margin. The margin is the physical distance between the closest examples of the two classes, as defined by the decision boundary. To maximize this margin and improve future accuracy, the machine must computationally minimize the Euclidean norm of the W vector. An SVM does not analyze context. It simply solves an optimization problem to find the widest possible gap between two data clusters. What happens when the target is not a discrete label, like +1 or -1, but a continuous real number, like a house price valuation? For this, we use linear regression. Linear regression is a predictive algorithm that learns a model represented as a continuous straight line or surface. This graph shows the geometric difference. Regression draws a line directly through the points, positioning it as close to all training examples as possible. A new input feature vector is mapped straight to the corresponding target value resting on the regression line. To find this optimal line, the algorithm minimizes a cost function called the empirical risk. Empirical risk is the average of all the penalty scores obtained by applying the model to the training data. In linear regression, this specific penalty is the squared error loss, which calculates the squared difference between the true target and the predicted value. Whether separating classes or predicting continuous values, supervised learning is universally driven by minimizing a strict mathematical loss function over a spatial dataset. If the model is a rigid geometric surface, optimized entirely for past data, why does it successfully predict the labels of future, unseen examples? This chart shows a mathematical function, which serves as the visual basis for probability distributions. The algorithm's predictive success lies entirely in a core statistical assumption about reality. We assume that new data points are drawn from the exact same probability distribution as the original training data. A probability distribution is a mathematical function that provides the likelihood of occurrence for different possible outcomes. Geometrically, if the statistical distribution is identical, new examples will naturally fall into the exact same geometric subspaces as the old examples. Because the new points cluster near the old ones, our pre-calculated decision boundary will, with high probability, continue to separate them correctly. For statistically unlikely outliers, the rigid model will make errors. However, because the algorithm maximized the margin, the number of these errors is mathematically minimized. A machine learning model's predictive power is entirely reliant on the future statistically mimicking the past. If the underlying probability distribution shifts, the geometry breaks. We have stripped away the 1959 marketing language of learning to reveal the strict mechanics beneath the surface. Converting real-world concepts into fixed feature vectors is the mandatory first step of all machine interpretation. Training an algorithm is nothing more than calculating the parameters W and B to satisfy a geometric cost function. That optimal plane remains useful to us only because of the strict laws of statistical probability. True mastery of artificial intelligence begins the moment you stop treating algorithms as synthetic minds and start treating them as hyperdimensional